All right, let's do an example of the Bernoulli equation. So the name of the problem kind of tells you which equation we're going to need, right? There's a lot of equations this semester, so kind of nice when the question tells you what's going on. All right, so we have a little system shown here where water is going to flow at a rate of 20 liters per minute, and we want to estimate the pressure required at point 1 if frictional losses are negligible. Now, it's kind of hard to see on my screen, but hopefully you pull this up on your end. This is 50 meters here. We have a mass 1 starting here, and we have a 0.5 centimeter inner diameter tube. We have the velocity, or not the velocity, excuse me, the volumetric flow rate of 20 liters per minute, and we don't know the pressure. And then we've got a 1 centimeter inner diameter pipe over here, a pressure 2 of 1 atm, and a mass 2, and we know that the density of water is 1,000 kilograms per meter cubed. So, because frictional losses are negligible and there is no shaft work being done on this system, this is an indication that we're going to use the Bernoulli equation, not just the fact that this equation or this problem is called the Bernoulli equation, right? This is how we know for sure that we can use the Bernoulli equation. No shaft work, no frictional losses. All right. So let's go get the Bernoulli equation. There it is. So a change in pressure divided by a density plus a change in velocity squared divided by 2 plus g delta z should equal 0. And here we're looking to find P1. We want the pressure required at point 1 if frictional losses are negligible. So let's grab our equation and let's write it as P2 minus P1 so that we can remind ourselves. And let's bring the velocity term and the positional term over to the other side. And then let's grab what we have in our system. We know that delta z is 10 meters, that's given. We know P2 is 1 atm, that's given. And we need to find a change in velocity in order to be able to go forward with this problem. We have everything else. So remember that when we want to find v squared or v in a system, remember that velocity is equal to volumetric flow rate divided by the cross-sectional area of the inner diameter of the pipe. And that's going to be pi r squared in any given system. Remember, you can remember this or write it down on an equation sheet, but you can also just look at your units, right? That's how you remember how these three things are related, by looking at units. So let's do that. Let's take our 20 liters per minute and let's make sure it is in terms of meters cubed. So let's convert. And then this is going to be our component related to the volumetric flow rate. And then I'm going to multiply instead of dividing to make sure that I've got everything in the right units. But here's the area calculation down here. We have 0.25 centimeters, and that centimeters is squared here. So if we're converting from 100 centimeters to 1 meter, we also need to square that quantity. So just don't forget that. And then I'm also converting from 1 minute to 60 seconds to put myself into some better units so that I get a velocity in terms of meters per second. So if we do that, we find that the velocity 1 is 17 meters per second in this system. Now, we could do the exact same thing for V2, but let's take a look at what's going on in the system. V1 must be equal to V2, and these are volumetric flow rates, right? Not the velocity, because the mass coming in is the mass coming out. There's nothing that indicates that we would have chemical reactions or accumulation in the system, and the density is the same. So V1 and V2 from the volumetric flow rate will be the same, meaning that we can find V2 by the same method. We're just changing the radius here. So I'm not going to show that full calculation. All the numbers, the only number that changes is this one right here. And we can find that V2 is 4.24 meters per second. All right, now that we've got that, well, let's do a change in velocity. So remember that a change in velocity, each of these terms need to be squared. You're not squaring the entire change. That's important. So let's square our second velocity and subtract the square of our second velocity. And look at that. We actually get a negative velocity here. And that might be a red flag. And you might think, well, why is that happening? But remember, this is a change in velocity. So what this is telling us is the water is slowing down, which actually makes sense if you look back up at the problem. If you think about having a really, really small pipe and then all of a sudden the area gets bigger, that water is going to slow down because the pipe is bigger. So that actually makes a ton of sense that we got a negative number, because that's a change in velocity, not a velocity itself. So just keep that in mind. All right, so now that we've got our velocity, let's flip on over and solve. So let's put in our pressure of 1 atm. Let's put in our new velocity. Let's subtract off g and 50 meters. So we also know that the density is 1,000. So we start to solve. And as we go along, we realize, ooh, this is starting to look a bit strange. What's going on with this pressure? And we can't have an ATM of this. That doesn't make any sense. So we actually have a problem with units here. So one thing that's important is ATM is not an SI unit. Everything over here is SI units. ATM is not. So we needed to be careful because in this case, we want to remember that one ATM is the same as 1,000 and 101,000, there we go, 325 pascals. And a pascal is the same as a Newton per meter squared. That's an SI unit. Okay, so that's why this math is not working out the way that it should, because we're using the wrong units for pressure. And that's going to be a stumbling point sometimes. So just make sure that you have this written down. I will give you this unit conversion when we're working on an exam. So we should really have this right here. So instead of 1 atm, we're subbing in right there. And so then what we get out of the system is a pressure of 456,325 pascals. And if we wanted to put that in terms of ATM, we're going to get 4.5 ATM. So that's kind of important here. Watch your units as you're doing this. We normally are using SI units because we're normally using 9.81 meters per second squared. So just keep your eyes on that as you're walking through these problems. Okay, so some real quick takeaways to recap. Don't forget your units, right? We just talked about why. And the other thing to kind of recap and make sure that you understand is make sure that you remember this relationship right here. How is volumetric flow and area related to velocity? Watch your unit conversions here. Make sure things are squared. And then when you take the difference, remember, you square each velocity separately. Okay, don't write V2 minus V1 and square the whole quantity. Okay, this is wrong. Don't do that. Okay, so make sure that you're watching this right here. And that's going to sum us up for our Bernoulli equation example.